Good morning. The next two lectures are very much connected, and our ultimate goal is to prove what's called the central limit theorem. As you can imagine by the name, the central limit theorem is super important, and in fact, it is the theoretical bridge between probability and statistics. So to get there, we're going to take a little bit of a side journey, and you're really not going to see why we're doing what we're doing until the very end. But let me at least give you a glimpse as to where we're going. So in this section, what we're going to do is start studying multiple random variables. So instead of just a single random variable, we're going to study a bunch of them. So why would I want to do that? Well, again, the central limit theorem describes how every distribution is related to the normal distribution. And the way that they're related is by a new random variable that we call x bar. And this x bar is defined as the sum of n independent and identically distributed random variables, and we're going to call this IID, independent and identically distributed random variables. So again, this guy is going to pop up in the central limit theorem, and because of that, we need to deeply understand this. But to deeply understand this, we're doing something different now. We're combining individual random variables to create a new one. So we're going to have to study that first to lay the foundation. So, what does that even mean? So just to give this a little bit more teeth, imagine that each xi is the weight of a randomly picked WWU student. So this new distribution x bar, what it's doing is it's randomly picking a Western student. And then it's going to do it again. Now, to make these independent, let's imagine that we have n copies of Western's population. So to be even more concrete, let's say we just have 3 copies. So I randomly pick one student from one copy, a second student from the second copy, and a third student from the third copy. I add those 3 values up and divide by 3. That gives me a number on this guy's distribution. If I do that again and again and again and again, I keep doing that, keep randomly picking 3 people, divide by 3, adding up the weights, then I can graph my results and I'll get a probability distribution for x bar. So that's what x bar is all about. And you may be thinking to yourself, oh, I've seen something like this before. I just add up the n things I have, divide by n. Sure looks like the mean that you would compute, for example, if you were finding your mean GPA, for example. And you're exactly right. This is actually a mean. All right, so we need to start digging into this. Again, you won't exactly see where we're going, but focus on understanding multiple random variables. So, in particular, let's start studying independent random variables. So you can have multiple random variables. Maybe they're independent, maybe they're not. We're just interested in the case that they are independent. And way back when, we said that if 2 events are independent, then the probability of A and B is the probability of A times the probability of B. All right, so let's now bump this up a notch. Let's consider 2 random variables, x1 and x2. And just to keep things simple, let's assume that these guys are discrete. In this case, if they're independent, we're going to define it in an analogous way. So for two random variables to be independent, the probability that x1 is some value and x2 is some value is going to be the probability that x1 equals x1 times the probability that x2 equals x2. And again, you play this game for n random variables. So we've seen this sort of thing in rolling two die. So for example, if both x1 and x2 happen to be uniform with m equal to 6, and you roll the die, with the probability that x1 equals 2 and x2 equals 3, well, that's just the probability that x1 is 2 times the probability that x2 is 3, or 1/6 times 1/6. So for that particular example, you might be thinking back in terms of events, but again, what I just described is something coming from a probability distribution. So let me give you another example, which is maybe not as concrete. Let's say x1 is binomial with parameters 10 and 0.5, and x2 happens to be binomial with parameters 3 and 0.8. And I tell you guys, oh, these things, whatever they're modeling, they're independent, and I want the probability that x1 is 1 and x2 is 3. Well, pause the video, see if you can find that probability. Okay, hopefully you paused the video and you said, oh, that's just the probability that x1 is 1 times the probability that x2 is 3. So then we just have to look at the individual distributions to compute that. So let's see, x1 is 1, so I guess 10, choose 1, 0.5 to the first, 0.5 to the ninth. This is just binomial distribution. And for the second guy, we're going to do n, let's see, 3, choose 3, 0.5, not 0.5, but 0.8 cubed times 0.2 to the 0. So that's what that probability would be. Okay, so now that we have a basic understanding of what these random variables might look like in terms of computing things, we're going to jump up a level in abstraction, and we're going to study the expected value. All right, well, definition, the expected value of some function u of x1 comma x2 is now the double sum. It's the double sum over both sample spaces. So I'm summing over all the x1s and s1, all the x2s and s2. U of x1, x2 times f of x1, f of x2, and actually let me give these guys subscripts because they could be different functions. So this is how it's defined if x1 and x2 are independent. Okay, so this might look a little bit intimidating, but if you think about it, it's really just the two-dimensional analog of what we did with expected values. This guy is this really is the probability that x1 is x1 and x2 is x2. So this is like our 1 PMF over there. And this is just some function of more than one variable. So u of x1, x2 could be x1 plus 3x2, or sine of x1 times cosine of x2. Now, if we had more time, we would actually be studying these multiple random variables probably for a solid week. But we don't actually have that much time. So what I want to do is focus on a couple of particular u of x1, x2 functions that are going to help us get to where we need to get to. So the ones that I'm interested in are sums and products. And the reason I'm going to be interested in sums and products is that will help me to find the expected value and the variance of that xbar creature that I put up earlier. Again, you can't see how at the moment, but I just want to let you know why we're doing what we're doing. All right, so again, sums and products. So we're interested in the following two functions. The first one is a function of two variables that can be expressed as a sum. There's a slight typo there that I want to fix. So an example of this would be u of x1, x2 is equal to x1 plus 3x2. So that's I'm writing x2 instead of x1. That's an example because this guy's a function of x1. This guy is a function of x2. And in fact, more to the point, as a second example, the one that we're actually really going to specifically be using is x1 plus x2. And I'll even tell you why. The reason is when we compute the expected value of x bar, remember we had x1 plus x2 plus x3 plus x4, et cetera, that's going to be related to this. So that's one thing we're interested in. The second one that we're going to be interested in is when we can articulate this function as a product of two functions of a single variable. So as an example, you have x1 typo here, this should have been x2, I wrote u2. U of x1 comma x2 is u of x1, where u of x1 is just x1, and u of x2 is just x2. So this guy here is just a function of x1. This guy here is just a function of x2. Okay, so each of these simplifies very nicely. Each of these simplifies very nicely so that they're actually super tenable to work with. So first off, let's see what happens then. So for one, let me actually write this out. So if I had this expected value, then by definition, that would be the sum over both sample spaces. This guy, u of x1 plus u2 of x2, times f1 of x1, f2 of x2. All right, so let's see what happens here. Let's see how we can simplify this. Well, the first thing I can do is I can distribute. So let me do that. I get same thing, the double sum. And I'm just going to distribute my f1 of x1 times f2 of x2. So I distribute that here. For the second guy, u2 of x2 times f1 of x1, f2 of x2. Okay. The next thing I can do is realize that the sum of a sum is the sum of the two sums. We actually saw that before a long time ago. So I can break this into two sums. So we have u1 of x1, f1 of x1, f2 of x2, plus the second sum, again, which is another double sum just copying these guys down. Let's see. On this side, we've got a U2 here, we've got an F2, and those guys both have X2s. That has nothing to do with X1. These guys are constant with respect to X1. So I can pull those guys out. So in other words, this becomes the sum over the sample space S2 of F2 of X2 times the sum X1 in S1, U1 of X1 times F1 of X1 plus the sum over my S2 sample space, U2 of X2, F2 of X2 times the sum X1 in S1 of F1 of X1. So I just pulled out what was constant with respect to the thing that I was adding up. Well, let's look at this. This guy, by definition, is the expected value of u1 of x1. So this is the expected value of u1 of x1. I could then pull this guy out, and I'm just multiplying it by 1 because I'm summing over the sample space for PMF. Same game here. This is the expected value of u2 of x2 times 1, because once again, I am summing over the sample space. So this tells me that when I happen to have a u of x1, x2, that's the sum, then it's a really easy computation. The expected value of u1 of x1 plus u2 of x2 is just, looks pretty complicated, that's just the expected value of u1 of x1 plus the expected value of u2 of x2. I can just add the individual expectations. So I said the u1 of x1 plus u2 of x2 that we're going to be interested in is actually just the functions u1 of x1 is x1 and u2 of x2 is x2. Well, this becomes a very simple process. You just have to add up the individual expected values to get the expected value of that joint distribution. And again, why am I interested in this? I'm interested in this because I actually want to look at this with x1 plus x2, et cetera, up to x sub n, and this will get me there. Okay, so that's the expected value of the sum. Typically, sums are easier to deal with than products, but it turns out that the product proof that we're going to go through is way shorter. So let's take a look at that. All right, so I'm now interested in the expected value of this guy in that special case where this happens to be a product of two functions. Okay, so this is u1 of x1 times u2 of x2, f1 of x1 times f2 of x2. Again, here I'm assuming that these guys are independent. So I invite you to pause the video, try to derive something from this using the same trick that we just used last time. In other words, pull out things which are constant with respect to the sum. So hopefully you gave that a shot, and looking here, I guess I can pull out this guy, and I can pull out this guy. So this becomes the sum let's see, u2 of x2 times f2 of x2 times the sum u1 of x1 times f1 of x1. And boom, we're pretty much done. This, by definition, is the expected value of u1 of x1. This is, by definition, the expected value of u2 of x2. So this tells me that if I'm looking for a product, so the expected value of u1 of x1, u2 of x2, then that's equal to the product of the expected values. And the one that we're going to be interested in is where these guys happen to be just x of I. So in other words, the expected value of x1, x2. Again, this is new distribution which is achieved by multiplying all of the xi's together. Maybe that's even hard to picture, but I know the expected value of it is just the expected value of x1 times the expected value of x2. Okay, so this is what we are really interested in. Those two statements are going to bring us one step closer, or actually several steps closer, to understanding the distribution of x bar. And we want to understand the distribution of x bar because we need to understand that so that we can eventually prove the central limit theorem. The central limit theorem, again, shows how every distribution is related to the normal distribution. So let me finish this lecture by giving you a quick example of this to see that even though the theory might be kind of tough, the application is not. So let's let x1 be Poisson. Parameter 3, x2 is Poisson. Parameter 9. I want the expected value of x1, x2, and the expected value of x1 plus x2. So pause the video, see if you can make sense of the result and what we have over here. Well, hopefully you gave that a shot and you said, oh, the expected value of a product. Oh, sorry, I needed to say that these guys, I always assume it, but I need to say it. These guys are independent processes. This proof relied on the independence. So if these guys are independent, the expected value of this product is just the product of the expected values. That's it. The expected value of the sum is just the sum of the expected values. And you're done. Again, this underlying distribution is this distribution with multiple variables. I don't even know how to picture that with Q Poisson, but I do know that I can do that computation. All right. I think that's enough for this video. I would recommend rewatching it if you need to. We now have all of the tools so that we can compute the expected value of x bar and the variance of x bar, and we'll do that in the next lecture video. So I hope you enjoyed this, and thanks for listening, and I'll see you next time.